Alright, so it's been a little bit again. I've still been working on it. I've just been kind of working on stuff that isn't very cool to show off. But I do have this to show off, so I did something. This is the Hermitcraft map again. It's a 4K by 4K import of it. And this is being rendered with Raymarching at 1080p on my GTX 1060. So this is without LOD. If I zoom in, you can see that everything is the highest level of detail. I do have it working, the Raymarching on my normal scenes with all the levels of detail, but it just, at least I've found, Raymarching does not scale as nicely with a level of detail as rasterization does. All that extra empty space you have to travel through with 26 levels of LOD really slows down Raymarching. Like, it's playable. I'm getting like 100 FPS in my normal scenes, which is good, but rasterization is just so much faster. Anyways, this is one example where Raymarching is way better. No level of detail as 4K by 4K import. And on top of that, Raymarching is a lot more fun to program and problem solve, in my opinion. Rasterization, the optimizations can get a little tedious. So now that I'm Raymarching through a volume, I do have to store the data on the GPU. I can't just only store a mesh. So what I decided to do is, first of all, I'm only storing the surface data. So if I go underground, you can see I'm only storing the voxels that are next to air. Inside the wall, you can see everything's hollow. I don't think this is a big problem though. I can't think of any reason why the GPU would need to know the volume data unless you're generating the world on the GPU. But if you're doing everything on the CPU, I think you can just keep the volume data on the CPU and send over only the surface volume data. So like how I'm doing here. This results in this entire map living in 240 megabytes of memory. That includes all of the palette data too. I'm just not rendering it on the screen right now. With the palette data rendering, so with things being textured and everything, the FPS is roughly 10% lower, which surprises me a little. I thought it would be quite a bit worse than 10%, but I'm not complaining. I'm just a little surprised. So if you'd like to try this build here, eventually it'll be in the main engine. I think I'm finally going to take advantage of this experimental features tab, and I'll put a little checkbox under if you want to render the scene with Raymarching. But until then, this build exactly is on my Patreon, so if you want to check it out with your own GPU, you can check it out on there. I did get this working on my integrated GPU, my Intel iGPU. You can see I'm getting at 1440p on an Intel iGPU, I'm getting 20 FPS, which also surprises me. I thought Raymarching would perform way worse on integrated GPUs, but I guess not. Something else to mention is I don't plan on using this Raymarching for the primary scene, so I'm not implementing any depth prepass or anything that really exploits knowing that all the rays come from the same point. I'm still going to be rendering the scene with rasterization, so I just don't want to include that. Okay, so you can see here, this is a program I wrote just to make iterating on the design of the algorithm a little bit faster. So this is a 64 by 64 2D chunk, and it has sparsity. So I chose a splitting size of 4 cubed. I guess before all this, I suggest go check out Douglas. He's where I got a lot of the inspiration from for how I store the data. Anyways, yeah, so the splitting size is 4 cubed, so you can see the initial chunk is split into these 4 big squares, so 1, 2, 3, 4. And then each of these can split into another 4, And then each of these can split into another 4. And then at this point, we're at the voxel level. So there's no more splitting, and it's the actual voxel storage. What else? The voxels are also stored sparsely. So only the voxels have the full resolution. Every other cell in this grid is only a single bit. And to find the data for a single voxel, you just do a bit count up into that point. We'll start with how the ray traverses the chunk at the highest level. So it's just standard DDA. So you can see the ray is initialized here, and then it just does DDA, a step into here, and then it's out of the chunk. So that's all standard. What changes with this sparsity is that you have to descend the ray down the tree and then ascend the ray back up. How I decided to reduce the amount of tree descension is, first I have a bounding box for every brick. So here you can see this 4x4 brick, this one here, has this green bounding box. First, when I try and descend the tree, I check against that bounding box, and if it doesn't collide, I just don't descend. And so you can see this is just normal DDA into here. I check the bounding box, it doesn't collide, so I do normal DDA again. And if it does collide, let's see, where is this? Here's an example. So if it does collide, I do descend the tree. And the cool thing is, since I'm already doing the ray box intersection, I know where the ray starts. So I don't have to DDA into here and then here and then here. I can just start the ray here. And while I'm checking the bounding box, I also test the far plane of the bounding box. So I know where it exits. So I don't need to go here, here, here. I can just go to here. And then at that point, I know that this is the last step. So I can ascend the tree and I can continue DDAing at this level. Something else that isn't implemented in this test system or this test project is the bitmask approach that Douglas has, his second optimization. I do it a little differently. So I have the start location and I have an end location already calculated from the bounding box test. And what I can do is there's 64 possible start locations, 64 possible end locations. That's a small enough amount that you can just store every combination of start and end location. You can store each one's potential voxel intersections. So here it starts right here. It ends over in this cell. And so it's only ever going to collide with voxels or sub-bricks that are within this bound. And so I pre-calculate all these at the program startup. Or all I need to do is fetch that mask and then AND it with the bit mask of this brick. And if it comes up 0, I can skip descending the tree. I don't have that here though, so that's why you see it's descended the tree here and it's done just DDA. That's it. Okay, now I want to touch on how I store it all in memory. So this is the storage for a single chunk. And first, every chunk has a 64-bit occupancy mask. So that's the most coarse grid that you saw in the last part. And then let me just put a dividing line to signify like different levels of the tree. How do I do this? Like this. All right. And then at the next level of the grid, so there's 64 bits, so that's 64 different children. So 64, and then all of them have an occupancy mask too. I don't store this one sparsely, so I store all 64 of them per chunk. It's barely any overhead per chunk to just not store it sparsely. And it saves from doing the bit count calculation. Okay, and then the next level of the tree, at this point, I do want to start storing things sparsely. So there's going to be n times 64-bit occupancy mask. And so at this point, since there is not a set amount on this layer, so I can't index into this implicitly. I have to actually store the index over here. So these also have, here, let me move this down a layer. 32-bit child offset. And so that offset is from this point, since this point you can determine implicitly. And then finally, the last layer is the actual voxel data. So palette compressed voxel data. And this as well, it can't be determined implicitly, so we gotta store here, we gotta store the 32-bit voxel offset. And so that offset is from this point here. This point, though, isn't determinable implicitly, so we do have to store where this line is, and we do that, or I do that, in the header here. And so this will point to where this resides, and then each of these offsets are from this point. So this is everything except I also store the bounding box. So instead of 32-bit child offsets, I store a 12-bit bounding box, and then a 20-bit child offset. Same thing here. All right, so let me get some drawing. So this 32-bit start index, this points to this line, the start of the voxel data. These child offsets point into here at different offsets. And then these child voxel offsets points into here. And that's what I decided to go with. I think that's it for this video though. If you do want to try the Raymarching, it's on my Patreon. And if you just want to wait, it'll be on the main engine whenever I get to it as an experimental option. Alright, thanks for watching.